Hey everyone, welcome back. So this is a video on question 1 of homework 2. So we're just going to get started by setting up this problem. Let's just really read through this quickly. So we have two parallel plates of length 2L, and they're separated by distance B right over here. So the upper plate moves downward at a constant rate V. So constant is key right here. Then a fluid, as we can see below, fills the space between the plates. And the fluid is squeezed out between the plates. Determine the mass flow rate. We know mass flow rate is dm dt. And it also asks for the maximum velocity. And maximum velocity is V max. Under the following condition, and we're given two conditions. One is where the exit velocity is uniform, and then also when the exit velocity is parabolic. So this is the question that we're given. So right off the bat, we can see that it's a little bit different than having a fluid going into an inlet and then an outlet, right? So this is where we would have a fluid go in and fluid go out. Then we have the inlet and then the mass rate from the outlet, right? So we know that it is a bit different, and that we can have wall here, but it's different because we don't have anything going in, right? So we're actually going to first, as always, start with the conservation of mass statement. So let's just write it out right here. Conservation of mass. And by now, I hope you all know this by heart. It's something that we'll continuously be using, so it's very handy to have this down. We know it's dm dt, right? As always, dm dt is a change, the rate change of the mass in the system. Then we have the rate change of the wall. This can either be positive or negative, depending on whether it's entering or leaving the system. Then we have our rate mass change from our inlets. And then we have our rate mass change from the outlets, right? Also, another way to write this would be like this: in, out. I'm just going to use the above notation. For now, it's the same as in your textbook, so I just want to prevent confusion in that way. So right away, so we don't have the following. We don't have any mass entering or leaving from the wall. We also don't have an inlet, but one thing to note is that first we have two outlets. So if I can model this in a way that might make more sense, let me just erase this right over here. We can kind of assume we have a box, right? We have a box, and what's happening is as fluid is being pushed down at a constant rate, we have the fluid exiting here in either a constant, this is what a constant exit velocity would look like, or we have a parabolic exit. So these are the two kind of options we could have. Like we could have it going like this, leaving like this, or we could have it kind of leaving like this, right? So that's kind of what the scenario is showing. That means, let's take a look here. That means we don't have a wall, any mass leaving from the wall. We also don't have an inlet. So all we have are outlets, right? And as we talked about in class, we just need to be very careful about those negatives, right? So I'm just going to first leave them as without the minus sign, just so we can get that negative value at the end. So we have dm dt equals W out. And one thing to keep in mind is we have two outlets here, right? So using our summation, that would mean that we need to multiply this by 2 because we just have two outlets. So we need to account for that. So the change, if we actually divide both sides by 2, that means this would be 1/2 of the total change per outlet, if that makes sense. So we have essentially two outlets. Another way to write this would be saying we have two outlets here. So it's really important that we're keeping that in mind as we move forward. The only reason we can also do 2W out is because we know that these outlets have the same amount of velocity and mass going out, just because they're identical, they're mirrored. So let's continue with this. One thing to keep in mind also is that means we have W out here, we also have W out here, right? So what is causing actually this change? This displacement up here, as this velocity is going down, the displacement actually is resulting in this flow outwards, right? So we do want to write W in right here. So that means the change in the mass is caused by this displacement. And the change in the mass can also be measured by measuring this displacement. So we don't have any fluid coming in, but that means we can also model this dm dt, the change, as also the change of the mass from the above plate coming down onwards into this so-called box. We're just creating this imaginary box. So that's one thing to keep in mind. These two relations actually are key in solving this problem. So please keep this in mind right here. Great, so let's just go back to our box. One thing also, we know that we need the cross-sectional area, right? So we do have the length of this plate, which we know is 2L, right over here. Then we also need to know the width of this box or the plate, because we need the cross-sectional area of so-called flow, right? It's not really flow of a liquid, but it's flow caused by the displacement due to the plate pushing down, right? So we still do need that. And the question doesn't give it to you, but we're just going to say the width is going to be just W. And that is also handful or useful because we also have our height here, and we need to account for this bottom plate. We have a bottom plate right here, and we need to know this cross-sectional area right over here. So that's going to be B and then W. So we do have that cross-sectional area. So it's really important. We're going to write right here, width is W. It's denoted by W, and it's important to not confuse it by the mass rate, which is also defined by W. So those are indicated by the W in and W out. Great, so let's start with just writing some of the things that we do know. Now that we have our conservation of mass statements right over here that we just determined, the next step is to write down what we do know. We do know that for our W in, let's write it right over here, and W out. Right, so we know our W in. Let's just start with that. We always have these same expressions. We have the integral of rho, and we have the same density here of the fluid. So we also have the velocity in, and then we take the integral of the cross-sectional area of that flow, right? It's the same old, same old. And also for our outlets, we also have the cross-sectional area, right? We also have rho, we have the velocity out, and we also have dA. Another relation that we did learn in class is that we can equate it to several things using our flow, our Q. Also, another thing that we could do is to use the average velocity, especially that's useful for our constant velocities, right? But first, we don't know that this fluid is incompressible, which is something we do need to know. So we are going to just use this definition for now. So let's just start with our inlet flow. So we know that our cross-sectional area, we have the top plate, right? We have our top plate. And our top plate has a length of 2L and W, and these are fixed. The velocity doesn't change because first, it's given to us at its constant velocity. Not only that, but these dimensions don't change. So that's really important to know. So that means, let's just erase this right over here so we have more space. That means that we just have, we maintain rho, our velocity in, and it's multiplied by our cross-sectional area, which ultimately says 2L times W. And that's our cross-sectional area. So important to keep that in mind. Then let's move on to our W out. So this is a little bit different because we have, let's just draw our plates. I'm going to draw it like this. But as the plate is going down, we have two different exit profiles. We have either our constant, right, constant exit, or we have are parabolic, right? And the thing to note here is in the y direction, this is our y direction, right? If we're looking at our different points in the y direction, for the constant velocity, we can see that the velocity is the same, right? But as we actually take a look over here, as we move up and down on the y direction, we can note that the velocity is not the same. So to use an average velocity, as I was talking about earlier, would be a good approximation for scenario A, but for scenario B, it would be a very poor estimate of the velocity. So it's really important that we're using the integral. It's good to just use the integral because we'll still get the same answer for this, even if we do use the integral. So let's just keep that in mind. So what we are going to do is first clear this. We know that this changes based on the y direction, so we can pull this integral out. We know that the y direction changes from a height of b, so we can mark this as 0 and we can mark this as b. So that means we need to find the velocity changes from 0 to b. So let's go from 0 to b of the v out, right? And then we also need to put dA. One thing we do know is because the cross-sectional area is going to be simply this change in the y, right? Or b, y. And then we also have this fixed width right over here, right? We have a fixed width, we have a change in y, right? So simply dA is going to be dy times width. And we can pull this width out to the other side. We want to try to make our life easier. Great. So we have these two things. Now what we're going to do is we're going to equate these two using our conservation of mass statements that we determined above. So we have dm dt equals 2w out equals w in, right? So that's great. We're going to use this in relating these two. And it's really important because we want to find v out, right? That is our goal. We want to find v out. We also want to find dm dt. So it's really important that we're using the conservation of mass to first find what we do know, and then relating whatever we can to find what the question is actually asking for. So let's just go on with this. So we know this relation. What I'm actually going to do is I'm going to move things around right over here. So we have WN. Great. So we're going to move this right here, right row, VN, 2L times width, and that's 2 times row times width times this integral times dy. And the reason why we're not solving for this integral is because we have two scenarios. A, that it's constant, and B, that's parabolic. So we're gonna just leave it right now and use this entire expression for both scenarios. And the great thing is there are some things we can cancel out here. Cancel the 2, cancel the row, cancel the width. As you can see, we're left with a very nice expression. Vn times L equals the integral from 0 to b, v out, with respect to y. So we're left with this really nice expression that we can use later. So what I am going to do is I'm going to erase some things and move them so we have some more space. Great. So now that we have this expression, we can note that we have two different scenarios, right? We have a v out is a constant, right? And this, see what the slash is says to denote a constant. And then our second scenario, we know that v out is parabolic. Well, let's just remind ourselves, how do we define a parabola? Well, in the x direction, the easiest way would be to just go a x squared. Actually, I'm going to use a lowercase a because we have a b, capital B for our changing height. Then we have lowercase b x plus c, right? That's how we define a parabola. But if we just look up right here, let's remember that we're talking about the y direction. The y direction actually gives us our values. For example, like this, we can assume our exit velocity to be like this. We need to see the change in the y direction that gives us values along this curve, right? Great, so what we need to do is instead of using x, we need to use y. So by plus c, right? And then we're actually going to use that in our v out. Great, so now let's just go back with the constant. It's very simple. So the goal of this is to first find our v out and then be able to, so actually let me write it out. What is v out? 2. What is v max? 3. What is dm dt? Right? So first, to get v out, to answer that first question, we are going to use the expression right over here that we just determined right up here. And we're going to just solve for v out. So v in times L equals integral 0b v out dy. And just really quickly, what is the integral of a constant? It's very simple. You just add that y, right, to the front, and it would be y times v out, and then you take the integral with your given bounds, and you'll find that you can solve for v out. So you'll, in the end, your answer will be v out equals something. It's just moving around. We know v max is always at the center of flow. Luckily, the velocity out for this first example is a constant, right? So no matter your change in direction in the y, it will always be the same velocity. So we know the v max is just going to be the v out, right? In this case, just because velocity going out is going to be constant, right? Then we know dm dt equals, we can either use w in or we can use 2w out. Either one will work. The change, we can get either way. So you can use either of those expressions to kind of get the answer. You do want your answer to be in v out form. So you don't want to just leave it in that v in. So make sure you use that v out right here. Use this to find your dm dt. Great. So let's just do the same thing over here. What is v out? Well, to find v out first, we have these coefficients that we do need to figure out. So what is A? What is B? What is C? Well, how do we figure that out? Well, we have an expression for v out right here. And all we do is just simple math. We need to figure out, so let me draw this drawing again right up here. We have our 2 plates, and then we have some fluid, it's pushing down, right? But our velocity profile is going to be parabolic, right? So that's a hint right there. We have, with our no slip conditions, we know this is height of B, we know this is height of 0. So at a height of B, the v out at B is going to be 0 by the no slip condition, right? We know that. We also know v out at 0, position 0 right here, is going to also be 0 by the no slip condition, right? So with these 2 things, we can actually figure out some of these coefficients. So we know these 2, right? So that means we know v out. Let's start with the first one, v out. Sorry, let's start with the second one actually. V out is 0, then ay squared at 0 is 0, then times or plus by, and y is 0, so we have 0 plus c. So c is 0, right? Great, that's easy. Now let's just keep going. So we have v out now equals ay squared plus by, right? No c. Great, so we also know that at v out b, v out is 0, right? So let's try that. Let's go 0 equals a capital B squared plus bb. So we need to remember that this b right here is going to be height, right? It's not the coefficient, not coefficient b, right? They're not the same thing. So it's really important. We're really making that clear right over here. So what we're going to do is simply solve for the coefficient. You can choose a or b. I'm not actually going to work this out for you, but solve for either a or b. What is a or what is b? You just need to do one, right? And then we can solve the final coefficient once we actually take that integral. So now that we have our coefficients, what we need to do is put it back into this relation that we did earlier for this one. So let's actually, I'm going to create a new page, not a space right here. So we're going to just keep going. So we have the same expression right over here. Vn times L equals the integral from 0 to b, v out dy, right? So we know v out is equal to ay squared plus by plus c. All we're going to do is we're going to keep going. Vn times L equals the integral from 0 to b, ay squared plus by plus c. And then dy, right? So as you can see, we need to take the integral because, again, the flow profile changes based on the y direction. It's not constant. So we do need to take it for the most accurate approximation for this, right? Or not approximation, it's the exact value. So then the goal after this would be you want to figure out what v out is, right? So once you plug in this, you will be able to actually figure out the coefficients for a and b. So you're just going to work through this integral, and then you're actually going to use your coefficient. You know c is equal to 0, right? Then you know a or b, you know one of these two. And it's going to be a relation. So you're going to have b equals something, something, coefficient a, right? Or a equals something, something, coefficient b. So that way you're able to actually simplify and figure out the actual true relation of a and b. So once you know a and you know b and you know c, you're actually going to be able to figure out what is v out. And once you figure out v out, it's going to be pretty sweet. Then you know v out is a function of y, right? V out is a function of y. To get the v max, we know that it's in the center of flow. So if we have our flow, I'm just going to draw the flow profile. Here's the plates, here's the plates, here's our plates. If we know this is the case, right? And we know this is a height of b and this is 0, where is the center of flow? The center of flow is right here at b over 2. So to get the v max is equal to just v out at position b over 2. You're just going to solve and get that value right over there. So that's how you get v max. Lastly, to get dm dt, remember you can also do w in equals 2 w out. I do recommend that you just try the w out. I know you do need to take the integral, but it's really good practice. Please try it this way to find dm dt. Then you should find dm dt is equal to something, right? And it's going to be in terms of v in, velocity in, right? So please do that. And if you have any questions, please come to my office hours today. They will be from 5 to 6 via Zoom. More than happy to walk through this question too. So thank you for watching, and I hope you have a great rest of your day. Bye.